have Jeff Hicks, who will be telling us about revisiting homological mirror symmetry for toric varieties.
Great. Thank you very much for inviting me. So before we get to revisiting homological mirror symmetry for toric varieties, there's a short introductory talk. Hopefully this will be followable for everyone, and please feel free to interrupt me at any time if you have any questions. So I'll first be talking about mirror symmetry for CP1. So this is a story which has been told many times, and hopefully we'll be able to cover a lot of aspects of that which is relevant to this talk. So the mirror symmetry story for CP1 exhibits three different ideas in mirror symmetry which are going to be interacting for us. And the first one is Syz vibrations, so Lagrangian torus vibrations. The second one is that this is an example where we really understand what homological mirror symmetry should be. And the third one, which is really going to be the focus of the next talk, is understanding how mirror symmetry behaves under compactification. And I'll also talk a little bit about Lagrangian surgery, which is a tool that we'll be using in the next talk as well. So kind of the picture that I have for mirror symmetry on CP1, where we're doing complex geometry on CP1 and symplectic geometry on this Langdon-Ginsburg model, is that CP1 looks a lot like C star, except that you kind of, I don't know, pinch the ends off to make them closed. And on the other side, by mirror symmetry, what you're supposed to do is maybe make the ends extremely big or something. So let's start with talking about Syz vibrations. Hopefully most people have seen some version of Syz vibrations before. I'm going to mostly use this as a chance to fix some notations that I'll be using throughout the talk. So the principle here is that mirror spaces arise as dual Lagrangian torus vibrations. And what is that going to mean for me? We're going to start with Q, which is some choice of affine manifold. For the practice of this talk, or the purpose of this talk, that'll just be R. And for the purpose of the next talk, it'll mostly be Rn, but even more mostly R2. And as an affine manifold, what do I get? I get inside of the tangent bundle a lattice of integral affine vectors. And inside of the cotangent bundle, I also get a lattice. And one of the things that you know from symplectic geometry is that this cotangent bundle carries a natural symplectic form, and it descends to the quotient. So if I look at the space T star Q mod T star ZQ, that's a symplectic space with toric fibers, which are given by the tangent fibers which have been periodized, and it fibers over Q. And that's a Lagrangian torus vibration. On the flip side, I could look at TQ mod TZQ. So the cotangent bundle has a connection which comes from this affine structure, and therefore comes with an almost complex structure, which simply just takes the base directions and interchanges them with the fiber directions. That also descends to this quotient, and it gives me, I guess, a totally real torus vibration, where the fibers are given by the tangent fibers, which have been periodized. And the idea that we're going to be taking, or the perspective for this talk, is that mirror symmetry is the interchange of X with X check. So here I have some kind of symplectic space, and here I have some kind of complex space. Any questions so far? Great. I suspect that this is going to be familiar for most people. So what are some things that we're supposed to be able to pull out of mirror symmetry? Well, let's look at some predicted equivalences. So one predicted equivalence for mirror symmetry, and I apologize here, I have already flipped the mirror, is that Lagrangians on C star, Lagrangian submanifolds inside of the symplectic space are mirror to complex objects on the complex space. And here I've drawn the example that we get for when Q is equal to R. And let's see how we can kind of interchange some of these objects. So one philosophy on how these objects are interchanged is that we start with some kind of submanifold, some tropical submanifold of the base Q. Then to build a Lagrangian lift of this tropical object, I can look at its conormal bundle. So if I look at the conormal bundle to P mod the conormal lattice to P, that gives me a Lagrangian S1 inside of this C star over here, which shows that every kind of tropical object down here can be lifted to some kind of Lagrangian object on the left side. Similarly, on the right-hand side, I can take a lift by taking kind of tangents everywhere. So I could look at the tangent space to P mod the tangent lattice at P. It's a little bit deceptive. I get a point, and I guess a point is an example of a complex submanifold of X check. And so this gives us kind of a very naive way where we can take tropical objects from the base and compare them to Lagrangian submanifolds on the symplectic side and compare them to almost complex submanifolds on the right-hand side. Maybe a second example that you would want to look at is if you were to look at all of Q over here and perform this lift, then on the right-hand side, you get everything. You get TQ living inside of TZQ. So I guess if you take the tropical lift, the complex lift of the entire tropical line, you get the entire space. Whereas if I was to take the Lagrangian lift instead, I would get kind of the zero section of this SYZ vibration. And already you can see that there's some ambiguity about all the things which are being constructed here. So at the very beginning, when I took the complex lift of this point, why did I pick this particular point? I could have picked maybe any of all these other points over here. All of those kind of look like things which project onto the same thing. Similarly, when I took the Lagrangian lift of the entire zero section, why did I take that section of the SYZ vibration? I could have taken some other one, and that would have also kind of had the same tropicalization. So the story kind of works very well at first appearance, but clearly there's additional information that we're missing out on. So the place where this additional information comes out in is how we encode the geometry of complex submanifolds and how we encode the geometry of Lagrangians in symplectic geometry and algebraic geometry, respectively. So the homological mirror symmetry conjecture of Kontsevich says that if X and X check are mirror spaces, then the Fukaya category of X is derived equivalent to the derived category of coherence sheaves on X check. I will leave this object in a black box, but I will say a few words about the Fukaya category. So this Fukaya category is a A-infinity category whose objects are Lagrangian submanifolds, whose morphisms are given by Lagrangian intersection flower theory, and the composition of morphisms is done by counting holomorphic disks which show up. So if you have Lagrangians L0, L1, and L2, then the composition from Hom L0, L1 tensor Hom, oh, I think I have these backwards. I probably want tensor Hom L2, L1 to Hom L2, L0 is given by count of holomorphic disks with strip-like ends limiting to the intersections between L0, L1, and L2, and with boundary on those Lagrangians. So perhaps we should take a look at an example computation which kind of validates some of these mirror symmetry predictions. So here I've drawn Lagrangian L1, and I've drawn a Hamiltonian push-off of that Lagrangian, L1 prime. If I compute the Hom between these two objects in the Fukaya category as a vector space that's spanned by two generators, E and X, or maybe I'll write that as a chain complex with a generator in degree 0 CE and a generator in degree 1 CX. And there are some holomorphic strips which we should count going between these. They have equal area and opposite sign. So in total, the differential ends up being 0. So if you were to look at the flow homology of these two Lagrangians, you would see something like the cohomology of S1. On the flip side, if you were to compute Hom in the derived category of sheaves between the skyscraper sheaf living above a point in itself, in this case, you would get the self-ext of the skyscraper sheaf, which you can compute by resolution. And if you were to compute this ext of OZ with itself, you would again get something that looked like H of S1. I guess the second example to look at is when you've disjoined these guys from each other. This is a little bit easier. So if L0 and L1 are disjoint from each other, then the Lagrangian intersection homology of these two guys is 0. And if these sheaves are disjoint from each other, they have disjoint support, then the sheaf homology between them is also 0. Okay, so what's a slightly more difficult computation? Let's compute something like the Lagrangian intersection flow theory between the 0 section and itself. And this is where things become a little more interesting. So because this Lagrangian is non-compact, in order to compute its Lagrangian intersection flower theory, I have to tell you what to do with the non-compact ends. So we need to control the behavior of these non-compact ends. We're going to require L to be maybe in this context parallel to the zero section at infinity as the requirement for our Lagrangians. We're going to require them to kind of be like the zero section as we go out to infinity. But to compute their Lagrangian intersection flower theory, I'm going to do a very funny thing. I'm going to take one Lagrangian and I'm going to wrap it as it goes off to the ends. And to compute Hom between L, L prime, and L, we wrap the first component. The reason to do this is to ensure some kind of compactness of holomorphic disks. So no holomorphic disk can have kind of a non-compact size because it has to get past all of these wrappings, and it's not possible for it to do so. So in this particular example, if I was to compute Hom of L prime and L, I would get a graded vector space with generators indexed by the natural numbers. Let's just kind of arbitrarily decide to call one of these generators 0. And we'll call one of the generators 1. And we'll label the other generators with monomials. And we see that as a vector space, this self-Hom of this Lagrangian looks something like Laurent polynomials, one variable, which is all very good, because if we were to look at the mirror space and we were to compute something like Hom of O of C star with O of C star, we would also get that this is Laurent polynomials. One of the more difficult questions is understanding what the composition is. So this is supposed to be not just some graded vector space that we get out, but we're also supposed to have the category, the structure of a category. So here I've drawn the Lagrangians L and L prime inside of the universal cover of C star, and kind of all their respective lifts. And now I've drawn a third Lagrangian, L double prime. And the relationship between L, L prime, and L double prime is that they're each more wrapped than the previous one. So L hasn't been wrapped at all, L prime has been wrapped with a slope of 1, and L double prime has been wrapped with a slope of 2. So if we were to look at kind of the original generators that we had, so recall that we indexed the intersections between L and L prime with monomials. Now let's kind of do the same thing with the intersections between L double prime and L. And we can see, if you were to kind of count this index appropriately, that something like 1 times 1 is going to be 1 on the intersection between L and L double prime. But if I was to take 1 times Z, I would get something like the intersection Z between L prime and L double prime. And if I was to take 1 times Z inverse, I get something like Z inverse on the intersection between L prime and L double prime. So we see that the Lagrangian intersection flow theory between L prime and L double prime, between L and itself, has exactly the same algebra structure as the ring of functions on C star. I feel like I've said quite a few things quite quickly, and I'm afraid I'm in the area, though, where people who are experts in this field believe everything that I've said is kind of very clear, and somebody who's maybe just entering this field might be kind of extremely confused by the pictures that I'm drawing. So I'm going to take a small break for questions. Okay. I'll move forward then. Okay. So the last component that we need to talk about is how does SYZ play with compactification in this story. So right now, I've told you that the Fukaya category of C star is the same thing as the derived category of coherent sheaves on C star, or maybe you believe from the last few pictures that that's the case. And now we want to figure out how we can get from this picture to the derived category of coherent sheaves on CP1, which arises as a compactification of C star. On the mirror side, this is supposed to correspond to looking at the Fukaya category of C star equipped with the data of a stop. There's kind of a picture or a mnemonic that I have for this. I have no idea if this picture or mnemonic is actually rigorously tied down in mathematics or mathematical physics. My picture for this is that if you took C star, it looks kind of relatively flat. And if you kind of imagine that you compactified it to CP1, you've made the ends of this kind of SYZ vibration very small. On the mirror, the thing that you should do is you should make the ends of the SYZ vibration very big in the places where on the B side you made them very small. And as a result, if you had a Lagrangian which was kind of going out towards this end at infinity, the end is so big that you can no longer try to wrap around it when you get out here. So you should not kind of continuously wrap your Lagrangians. At some point, the end is so big that no matter how hard you try to wrap, it's impossible to do so because you've blown up the end to be of such a big radius. Anyways, this category over here is going to consist of Lagrangians, which are not allowed to wrap as we go off to the ends. So I need to tell you a little bit about what these partially wrapped Fukaya categories are. Well, what they are is, in kind of a very fast outline, is they're a category whose objects are Lagrangian submanifolds which avoid Lagrangian stop in the boundary of my space. So the Lagrangians that I'm going to consider have to avoid some pre-specified Legendre that I've tacked on. And the homomorphisms are computed by wrapping up to the stop. So if I wanted to compute, say, the Lagrangian intersection flower theory between this red Lagrangian and this blue Lagrangian. So maybe let's make them parallel. So if this is L0 and this is L1, and I want to compute CF L0 L1, then in order to do that computation, I have to take this first component and wrap it to the stop. So L1 stays roughly where it is, but L0, I guess, gets pushed around, so it gets wrapped to the stop on this side, and similarly gets pushed around on the other side. So that it wraps around once. So the direction of wrapping that I'm considering is wrapping upwards on this end and wrapping downwards on this end. And after I've instigated that wrapping, now L0 and L1 intersect at one point. Any questions about this picture?
We're going to have a break in 3 minutes, so maybe we'll...
Yeah, great. I have kind of just one or two more slides, and then we'll be at a good place for a break. Okay, so let me then describe kind of the entire homological mirror symmetry for CP1. So start with a line bundle, O of n. This gives me the data of a support function, phi from R to R, which is a piecewise linear function, which is 0 mostly, and then has a component of slope n. And then from the data of the support function, I can build a Lagrangian, which is roughly taken by taking the exterior derivative of that support function, thinking it of as a section of T star Q, and drawing it down. In this particular example, the line bundle O of n gets mapped to the Lagrangian, which wraps around n times before being wrapped up to the stops. The last thing that I want to say before getting to the main portion of the talk is, what about the kind of Lagrangians that we had before, which were mirror to points? Well, you could understand those Lagrangians by understanding the mirror, the mirror, where on the mirror we have an exact sequence between a line bundle O minus 1, O to the skyscraper shape of a point Z, if I was to draw the Lagrangians, which are mirror to O minus 1 and O, they would be this green Lagrangian over here, this red Lagrangian over here. And you notice that if you take kind of the symmetric difference between the red and the green Lagrangian, you get an SYZ fiber of your vibration. So maybe we think that the symmetric difference operation is similar to taking an exact triangle on the mirror, and we think that this Lagrangian fiber, FQ, is mirrored to the skyscrapers above the point. So that gets us kind of most of the points of CP1. There are 2 points which don't show up as SYZ fibers, which are the points above the North Pole and South Pole. So the last objection that you might have is, well, how do you construct the mirror to the point that lives above the North Pole or the South Pole? Well, you could draw the same picture, but instead of kind of wrapping the things initially, you could leave a little bit of a gap here when you took the symmetric difference. Kind of remove this portion between those two Lagrangians. So that when you took their symmetric difference, you were left with something like this. And then you could apply a Hamiltonian isotopy to get a little Lagrangian which wrapped around the stop. So this small Lagrangian, which is called the linking disk of the stop, is a potential mirror to, say, the skyscraper sheaf of the North Pole. Okay, I think I'm at 30 minutes for the short introductory talk. I apologize that that went a little bit quickly, and let's take a break for questions.
Okay, thanks, Jeff, for that. We already had one question a few minutes back from Hank Chen. Would you mind unmuting yourself and asking your question?
Sure. Yeah, my question is just like, I'm wondering if you're you're considering Liouville domains now, right? Since you're putting Lagrangians at a boundary.
Yeah. Mm-hmm.
Okay.
Yes. Right, in practice, this machinery is designed to work, and I should say kind of more generally what this machinery is. So here we're using partially wrapped Fukaya categories, which have been implemented by Zach Sylvan and Ganatra Pardon-Shende. And that's going to be in the context of working with Liouville domains. And then the stops that you can consider are going to be Legendrians, which are in that contact boundary.
Okay.
And then the Lagrangians, which you're considering, are those which are cylindrical at infinity. So at the contact boundary, they need to be kind of parallel to the Liouville flow, and they need to look like a Legendrian times R.
Okay. And also another question, does the HOM that you've computed in the partially wrapped Fukaya category, does it depend on how you actually wrap around the stops, right? Because in the example you gave, you sort of have a specific direction at which the two sort of, you're wrapping one of the Lagrangians in a specific direction at each ends of the cylinder. What if I do it the other way around?
Yes, so that direction is specified to you by the structure of the Louisville domain, right? So that's going to be the direction of the rate flow.
Oh, okay. Mm-hmm.
So, yeah. You could, of course, do something like a little bit different. So different stops will give you different categories. So you could, for instance, work on something which was kind of only stopped at one end. So you could remove this stop, and then you'd be wrapping one side, which would give you a different kind of flow or theory computation than whether or not you had stopped both the sides.
Mm-hmm. Okay. Okay, thank you.
Okay.
Thanks for the question.
So are there any other questions that want to go on the record? If so, there's two types of questions. One will be recorded, and for the other type, if you're too shy to have your question recorded, I'll pause the recording and then we'll have unrecorded questions. Okay, it looks like there's no recorded questions. Let's pause them.
Great. So the second half of the talk, or the research portion, is on revisiting homological mirror symmetry for toric varieties. All of this is joint work with Andrew Hanlon, who's at the Simon Center for Geometry and Physics. Okay, so from the previous talk, we had the following setup, which was we were looking at the derived category of coherent sheaves on CP1 and comparing that to the partially wrapped Fukaya category for C star, where I had the data of this stop F, which was 2 points on the boundary. The comparison that we had made so far was that we had compared Lagrangian sections to line bundles, and by a couple of pictures, we maybe thought that those were actually computing the same thing. And we had a correspondence which was set up, which was you take a line bundle, you associate to that some support function, and you could build a Lagrangian section associated to that support function. Now, at this point, it doesn't seem like we've actually completed computing mirror symmetry. All we've done is computed it for Lagrangian sections. But at the end, there was some argument about knowing enough Lagrangians to conclude homological mirror symmetry. So I was able to show that you were able to build the fibers of the SYZ vibration by gluing together some Lagrangian sections, and that you were able to build some kind of Lagrangians at the end of the SYZ vibration by gluing together Lagrangian sections. And so just knowing homological mirror symmetry for Lagrangian sections was enough to recover homological mirror symmetry for everything. Now, the example that we're going to want to look at is extending this for torics instead. So instead of looking at CP1, we'll be looking at a toric variety X check sigma. In this example, everything is going to be, so sigma should be smooth and projective. And the mirror space that we're going to have is also going to be modified. So we're looking at the wrapped Fukaya category, sorry, partially wrapped Fukaya category of C star to the n, stopped at F checks at F sigma, which is some Legendrium, which I will describe in a couple of slides. And in this context, actually, the majority of the story that we had so far carries through. So this entire story of looking at line bundles, associating to them support functions, from those support functions building Lagrangian sections, this all holds out. And in fact, the Floer homology between these things matches well. So there's a good amount of literature on this, but I'll mention two names specifically. So this was proven by Abu Zaid in his PhD thesis, and Andrew Hanlon adapted this for a version of the Fukaya category that we're going to use later, the monomial admissible Fukaya category. Now, the thing which actually still needs to be proven is this last statement over here, which is that do we know enough Lagrangians from this matching to prove homological mirror symmetry for the entire thing? So this section about generating the Fukaya category, or is saying that Lagrangian sections tell you enough to conclude mirror symmetry is the problem which we're going to address. Now, there's actually like a good mirror symmetry reason why you would think that knowing this correspondence by itself is enough. After all, line bundles in the smooth setting generate the derived category of coherent sheaves. So if you believe mirror symmetry, then you should think that kind of knowing the data on line bundles is going to be enough to get you all the way. So let me describe what this stop is. So the stop that we're using is this FLTZ skeleton, Feng Lu Choiman as Aslo skeleton. I've written it over here just kind of in terms of the cones of this toric variety. So recall sigma, this fan, is a collection of cones in the base of my SYZ vibration, Q equals Rn. The C star n, which this thing is going to live inside, we thought of as being T star Rn mod a lattice. And so to each cone sigma, I can look at the conormal to that cone, or the positive conormal to the cone, which is the subset sigma cross sigma perp inside of C star Rn when it's been identified with T star Rn mod T star Z Rn. So that's giving me some Lagrangian inside of C star to the n. In order to obtain a Legendrian, I'm going to take that Lagrangian and I'm going to intersect it with the contact boundary. So the example for CP1, the fan for CP1 looks like this. The FLTZ skeleton will have 3 components, which look like these 3 Lagrangian subspaces. And the stop is just the restriction of all of this to the end. So FP1 is just these 2 purple dots. I'm going to now move on to the example which I'm going to focus on for the rest of this talk, which is CP2. So the fan for CP2 has 7 cones, 1, 2, 3, 4, 5, 6, 7. And I'll draw the FLTZ skeleton in 2 different projections of C star squared. The first projection which I consider will be to the SYZ fiber. So this is projection to a torus. And the second projection that we'll consider is to the SYZ base. In order to construct a component of this FLTZ skeleton, I look at one of my fan components and I construct the normal torus to it inside of the fiber. And inside of the base direction, I take the same direction. So this little fuzz over here is telling me that the associated Lagrangian is the conormal to the Lagrangian in the direction of the fuzz. Similarly, if I was to look at some other components, maybe this blue component over here, I would get a portion of the FLTZ skeleton which corresponded to this Lagrangian subspace. And if I was to look at this cone, then I would get the portion of the conormal fiber above the origin, which fills up this entire quadrant of the SYZ vibration. So maybe kind of the quick takeaway or sanity check to make sure that we're talking about Lagrangians, you can notice that the sum of the dimensions in the SYZ base and the argument directions is always real dimension 2. So these are giving us things which look like Lagrangians, so two-dimensional real submanifolds inside of C*². In total, this FLTZ skeleton has a few more components. Oops. Sorry, that one doesn't live there. That one lives over here. And one more component, which lives down here. Which kind of gets fuzzed over there. Finally, there's one more portion to the FLTZ skeleton, which is associated to the zero cone, which is the entire F0 fiber. Now, if I was to look at the stop of this, so this is describing this Lagrangian which goes out to infinity. If I was to look at the stop, I would take this entire subset and intersect it with the boundary at infinity, and I would see kind of 3 circles. Let me color them. Red, blue, and black that are linked together by 3 edges. Which you can see is kind of the boundary behavior of this skeleton in this SYZ picture. So why will this end up giving us homological mirror symmetry for the toric variety? Well, let me tell you about some previous work. So the strategy that Andrew Hanlon and I are employing is kind of twofolds. The first one is to look at kind of existing results about mirror symmetry for toric varieties and interface it with the partially wrapped Fukaya category, which is stopped at this FLTZ skeleton. So on the previous slide, I told you that there was a story about the subcategory of line bundles matching the subcategory of Lagrangian sections. That was kind of worked on in Abu Zaid's thesis and by Andrew Hanlon. Both of these subcategories inject into the derived category of coherent sheaves, and in our setting, what is called the monomial admissible Fukaya category for sigma. Now, in the first part of this project that I'm working on with Andrew, we construct inclusion of the monomial admissible Fukaya category for sigma into this partially wrapped Fukaya category. So we're allowed to use kind of machinery to talk about partially wrapped Fukaya categories to handle homological mirror symmetry. The question remains, does the category of Lagrangian sections generate? Because that's the only part which we've constructed this injection for. The idea is as following. So if you were to prove generation of the category of coherent sheaves, then you would use the following facts. The first fact that you would use is that if you look at the category of line bundles, they generate the gross empty group of the derived category of coherent sheaves on extract. And then there's a second fact that you have to use, which is that in this particular setting, knowing that you're able to generate the gross empty group is enough to show that you generated a derived category of coherent sheaves. So this is the type of strategy that we're going to want to mimic on the mirror. So the first thing that we're going to want to show is that Lagrangian sections generate the derived category of the Fukaya category, sorry, the gross empty group of the partially wrapped Fukaya category stopped at this FLTZ skeleton. And the second part is we'll use a result of Ganachal part and Shenda, which says that in this case, a generation of this guy is equal to generating linking disks of the stop, which implies the generation of this entire Fukaya category. So the proof that we're taking over here is kind of very inspired by mirror symmetry. We're really trying to port over as much of the machinery that we can have. And then it kind of gives us kind of another interesting interpretation of this GPS generation criteria as kind of being maybe the mirror statement to this fact that you can generate the derived category of coherent sheaves once you're able to generate K naught in this sense. Okay. I seem to have skipped a slide while writing. I gave the proof strategy on the previous slide. So maybe this is a good place for me to pause and see if there are any questions. Okay. Then I'm going to go ahead and draw kind of a picture proof of this generation. Oh, Elsa has a question.
Sorry, I was hitting the space bar to unmute, but instead it was just typing a space to everyone. How the statements on the coherent sheaf side, how does that work? Generation of K naught implying generation full stop.
I must confess, I don't know the proof of why generation by K naught implies the generation of a DB-Co in this setting. If you look in Muhammad's thesis, it's listed there, or the citation to it is listed there along with the argument for why it works in the particular case of toric varieties.
Okay, cool. Thank you.
So let me give a kind of a picture proof for generation. So the picture proof for generation is the following. So we have this FLTZ skeleton. And we want to show that we can build a small Lagrangian disk which intersects this FLTZ skeleton at one point. From here, GPS tells us that if we can build all of these disks, then we can generate the Fukaya category. The method for building the disk is the following. So we start by taking a Lagrangian. We start by taking a tropical Lagrangian. And the projection of one of these tropical Lagrangian sections will be a region that fills the argument projection like this. So this is the argument of d phi tilde for some phi from R2 to R. We then take a slightly different Lagrangian section. So take something argument of d phi tilde prime for some different support function. And the difference between these two support functions will be that one support function has a section which extends a little bit past the skeleton, whereas the first support function has a section which does not extend past a portion of the skeleton. And then by taking one of these symmetric difference arguments that we employed earlier, we're going to obtain a new section, this orange Lagrangian, L, which lives nearby the skeleton. So the procedure looks kind of very similar to the procedure that we had at the beginning for building that little U-shaped Lagrangian that lived near the end of C1. So recall that picture was, I built a little Lagrangian U that lived near the stop by taking two different sections and surgerying them together. And here we're just doing the same thing, but kind of with all the combinatorics of this skeleton. Now, as a picture, this is a nice way to see how you're building all of these little tiny linking disks to the FLTZ skeleton. You can see that there's a nice combinatorial game where you can take kind of different Lagrangian sections which kind of encompass various different portions of this diagram and kind of serger them together and patch them together to build all the little linking disks that you would want. However, actually kind of proving generation this way in explicit coordinates is a bit unwieldy. Ideally, what you would like to have is you would like to have some kind of inductive argument that would allow you to build all of these. So let me give you a precise definition of how we build them and a statement on the inductive argument that we use. So the tool that we use to build these Lagrangians are called Lagrangian cobordisms. They're Lagrangians. A Lagrangian cobordism in X is a Lagrangian cobordism is a Lagrangian in one dimension higher, X cross C, which has ends that limit to a specified set of Lagrangians. So what do I mean by this? An example of a Lagrangian cobordism between, say, L0 and L1 to L2 would be a Lagrangian submanifold K inside of X cross C. Here I've drawn the projection of K down to the C coordinate, and we require that at the ends of C, my Lagrangian cobordism looks like L2 cross R. I have L0 cross R over here and L1 cross R over here. So when I say that I can build one Lagrangian out of other Lagrangians, I will mean L0 and L1 build or generate L2 if there exists a Lagrangian cobordism from L0 and L1 ending on L2. The reason that we say that this generation holds is because there is an algebraic result of Biron and Cornea that says that whenever you have a Lagrangian cobordisms with left ends L1 through Lk and right end L0, then the Lagrangian L0 is generated by the right ends. So, for example, there exists a Lagrangian cobordism whose ends are these three Lagrangians over here. So I have my indexing a little bit different. L0, L2, and L1. So this tells us how we're going to be building these Lagrangians. We're going to be building them by using these Lagrangian cobordisms. Now I'm going to tell you kind of the step that we're going to use for the inductive argument. So a way that you can go from kind of, you can build maps between symplectic manifolds of different dimensions, or you can build relations between Lagrangians in symplectic manifolds of different dimensions, is to use a Lagrangian correspondence. So a Lagrangian correspondence is a Lagrangian inside of the product of two symplectic manifolds, where the symplectic form has been flipped on the first factor. So example of one of these is to take kind of a symplectomorphism between two symplectic manifolds, and then the graph of the symplectomorphism gives you an example of a Lagrangian correspondence. The main reason that we're going to be using Lagrangian correspondences is because they have a composition tool which allows you to take Lagrangians in the target symplectic manifold and transfer them to Lagrangians in the domain symplectic manifold and translate them to Lagrangians in a target symplectic manifold. So given some Lagrangian in X0, you can obtain a Lagrangian in X1 by taking a geometric composition, which is you take L0, you pull it back, you intersect it with L01, you push it forward. So this operation is kind of mirror to Fourier-Mukai transform, where you take a sheaf, pull it back to X0, tensor it, and then push it forward to X1. Now, the reason that we're going to be using these correspondences is that they're believed to have some kind of functoriality. So on the Fukai category, if I give you a correspondence L01 from X0 to X1, it's believed that there's a corresponding functor that you get from the Fukai category of X0 to the Fukai category of X1. This is in general really hard to prove. The holomorphic curve theory is quite difficult to do. However, on the Fukai category, on the K group of the Fukai category, this is much easier to prove. That whenever you have a Lagrangian correspondence, you do in fact get a map from the K theory of the Fukai category of X0 to the K theory of the Fukai category of X1. And the reason is because correspondences preserve Lagrangian cobordisms. So the result of Biron and Cornea tells us that this K theory of the Fukai category is encapsulated in the Lagrangian cobordism classes of the Fukai category. And because correspondences preserve cobordisms, we get a map between these two objects.
Jeff, just as a gentle reminder, you're a little bit over time, so if you could. No, it's fine. If you can finish in a couple of minutes, because we have a little bit of a gap between now and tea, so there's time to continue. But
I apologize for going over. Great. Let me kind of hit the two main steps, and then I'll be out. Okay. So what's the main idea that we have? The main idea that we have is that there's on the B side, there's an inclusion that you could do to say a toric divisor inside of P2, including into P1. What Hannah and I do is we construct a Lagrangian correspondence from the mirror to P1 to the mirror to P2. Which is mirrored to this inclusion. Then by the first slide, or sorry, by the first presentation, we generate the mirror to P1 with Lagrangian cobordisms. And then we push just generation along the correspondence. So all of this depends on kind of proving that many expected mirror symmetry properties hold between the inclusion of a divisor into P2 and this Lagrangian correspondence, which is supposed to be mirror to the inclusion. As a quick picture, and maybe I'll end my presentation on this slide, you can kind of diagrammatically go and show that you can generate the mirror to P2 by inductively applying this surgery relation and pushing along these Lagrangian correspondences. So for instance, by starting with 4 sections on C star squared, you can surgery them together to build kind of 2 linking disks, which are the push forward of actual linking disks on C star. I feel like this last picture is probably not as helpful as it could be if I had more time, but I will stop there. Thanks.
Thanks, Jeff, for your talk. Does anybody have any questions? Right after this, we're also going to have a tea, so you can also ask Jeff more questions there. But are there any quick questions that people want to ask, recorded and unrecorded? Doesn't seem like they're recorded questions, so maybe we can try